Hello everyone. My name is Tausif from India. I am presenting my paper called titled "Learning to Classify Faster Using Spiking Neural Networks." This is a collaborated work. The other authors of this paper are Pranav Machingal, Sherin Dora, Suresh Sundaram, and Chinjak Men. The contents of this presentation are first we have an introduction about spiking neural networks and the opportunities in this area, and then we have the TSMS TDP learning algorithm proposed in our paper, which is a composition of architecture and the weight update algorithm learning algorithm, and then we have a performance comparison of this learning algorithm with other existing learning algorithms, and then we have a conclusion. So why spiking neural networks? So basically, because the spiking neurons resemble more to the biological neurons compared to the artificial neurons. This is one of the reason, and also they are computationally more powerful. As the biological neuron, which is shown in the figure, as it processes the information in terms of spikes. The spiking neural network or the spiking neuron also takes spikes as input and gives spikes as output. And then after constructing this spiking neural network, so there are so many applications of the spiking neural networks in so many machine learning tasks, such as classification, recognition, event prediction. Neuromorphic computing is the recent area where the hardware realization of the spiking neural networks are done on chips. And the opportunities or challenges in this area, mainly while considering the learning algorithm. There are two main basic learning algorithms in this area. One is the bio-inspired one, which is termed as synaptic time-dependent plasticity. In short, stdp. It is a complete local learning rule. It depends on the input spike of the to the neuron and depends on the output spike of the neuron. And the main backdrop of this learning algorithm is if there are if there are different features in the data set belonging to the different classes, but they are with high overlap, then this STDP, its performance is found to be decreasing. And then the other main algorithm is a gradient-based learning algorithm, which is proposed in 2002, known as spike prop. It is difficult. Evaluating gradient in the spiking neural networks is difficult as spikes are discontinuous in nature. The other problem is a silent neuron problem. If there is no spike, then no update. And then when coming to the in terms of architectures in the deep spiking neural network architectures, there are so many literatures available of conversion of trained ANNs into SNNs and also independent layer-wise training, but all these have high computational effort due to the longer simulation durations. As the number of layers increases, the simulation interval increases, and then the time required for making the decision is also required, is increased. Sorry. So, so we focused on this area to reduce the time taking for the decision. We focused on this area, so we proposed a learning algorithm where it just works on the first spikes of the neuron. We will see in the future. So, our proposed work we have divided into architecture and temporal separation modulated HTTP learning algorithm. Architecture has inhibitory connections in the hidden layers. It is a multi-layer architecture, and in the learning algorithm, at first we evaluate the cross entropy loss based on the temporal separation, and then we evaluate the sensitivity factor using gradient of this cross entropy loss, and then we update the weights with the sensitivity factor and STDP. We will see in detail in the upcoming slides. And first, before going into the architecture, the main component of this architecture, that is a spiking neuron, there are so many mathematical models available for the spiking neuron. We use the spike response LIF model, which is proposed in 2002 by Wolfram Jesner. And if there is a presynaptic neuron and postsynaptic neuron connected with a connection known as W pre, and some input synaptic spikes, input spikes coming from this neuron to the postsynaptic neuron, then a potential builds up in this postsynaptic neuron, as shown in this figure, depending on the V post T formula shown here. So when this postsynaptic neuron potential crosses a threshold, then this postsynaptic spiking neuron produces a spike at T plus 1. So in this figure, we can see if there is a single spike, how the potential builds up. If there are multiple spikes, how the potential builds up. Then this after generating a spike, this v post of t is reset to its initial value. Then again, if there are incoming spikes, then again the potential builds up, and it goes on. So with this spiking neuron, we use this kind of spiking neuron in a L layer architecture. So the input layer is used to present the input spike patterns, and there are L minus one hidden layers and L output layer. In the hidden layers, there are weights and inhibitory connections connected to them. And in the output layer, the number of neurons in the output layer are equal to the number of classes in the data set. And then each neuron is in the output layer is associated with a class in the data set. And whichever neuron spikes first in the output layer, then then the predicted sample will be the class associated to that neuron. So after this architecture, we will see how the learning algorithm updates the weights. So first thing is we use as we said, we use the modulated version of stdp. First, we go through what is stdp. So before going into stdp, there may be two cases in the two scenarios in this phenomena. There may be third scenario also where t pre equals to t post. It is also considered as diffusion. We will see that. So if the presynaptic spike occurs before postsynaptic spike, then it is considered that this presynaptic neuron is influencing postsynaptic neuron, and hence the weight in between them is increased. And in the other case, if the presynaptic spike is occurring after postsynaptic spike, then this presynaptic neuron is considered to be not influencing the postsynaptic neuron, and then therefore the weight in between them is decreased. And if both are equal, T pre and T post both are equal, then also it is considered to be depression. Then, based on this stdp, we will develop the learning algorithm. At first, we evaluate the error function based on a temporal separation. Temporal separation is just difference of the first spikes of the neurons in the output layer. K is any kth neuron, and K star is the first spiking neuron in the output layer. And depending on the ZK, error function is evaluated. This is called cross entropy loss, and tau d is the minimum spike interval required between these first spikes of these neurons in the output layer. And dk is, it will be 1 if the class represented by the kth neuron and input sample are same, otherwise it is 0. Then the gradient of this error function with respect to temporal separation is evaluated in the output layer for all neurons in the output layer. And then using this sensitivity factor, this gradient is called a sensitivity factor. And depending on this sensitivity factor, the all neurons sensitivity factor in the remaining neurons in the network architecture is evaluated. One pictorial representation is shown here for evaluating the sensitivity factor of a neuron, ith neuron in Lth layer. We require the sensitivity factors of all neurons in the L+1 layer. So in this scenario, with the help of this, we are transferring back propagating the error information into the hidden layers. Now, after evaluating the sensitivity factor, we combine the sensitivity factor with the stdp to update the weights. Whether there is inhibitory weights or there is feed forward weights, both are used along with stdps. So this global error information is combined with stdp to update the weights. Now this algorithm is evaluated on the MNIST data set, and its performance is compared with fully connected neural networks and also convolutional spiking neural networks. The performance of TSM STDP is almost on par with the fully connected neural networks. And but here TSM STDP does not convert the input data set into some binarized version, whereas the other temporal SNN converts that MNIST, where there may be a loss of information due to that binarized version of MNIST dataset. And also this BPSTDP, the other FCNN, fully connected neural network, requires computation at each and every time step, where TSM-STDP does not require that. Now, coming to convolutional spiking neural networks, even though they are 2% better, they require computation over entire simulation interval. Whereas TSM STDP, we can stop the simulation once we obtain the first spikes of all the output neurons. So on an average, if 900 milliseconds is the simulation interval, then on an average, just 145 milliseconds are required for making a decision. That's how we classified faster when compared to the other learning algorithms. So again, its performance is compared on other real-world ADHD data set. And the learning algorithm is compared as projection-based learning. There are two main feature extraction techniques. We compared our learning algorithm with the best performing feature extraction technique, and we found that our algorithm is on par with the other algorithms. Now, coming to the conclusion, so we provided a learning algorithm depending on the temporal separation of the neurons, that is time difference between the neurons for deep SNN architectures. And also it combines the back propagation and also stdp, the fusion of global learning rule and local learning rule we can see here. And then it is also suitable, it is faster, suitable for faster classification, as we can interrupt the simulation once we obtain the first spikes in the output layers. And then we have also seen that it is capable of handling real world classification problems. Future work, we'll expand this proposed learning algorithm for more complex data sets, and we'll expand the more we'll see the more scope of this learning algorithm. Thank you.